Well, thank you, Dusa, for the kind introduction, and I really would like to thank the organizers for the invitation. So Margaret Reddy told me that I could make a little comment or little tidbits each day. And so my little tidbit for today is that I think in mathematics there's this myth of individual genius, and that people are either a genius or not, and you either succeed because you're a genius or you don't succeed because you're not a genius. And I think that this is absolute nonsense. I think mathematics is a community effort, and we do things together. That's one of the things I love about working in industry. We make more progress when we work together. And we don't get anywhere without the support of others. And the organizers of this program have given their time and energy for years to run this program. And I just think that is so amazing. So I think we should give the organizers a round of applause. So I also have something a little unusual for a math talk, which is I have some props. So these are things which I would like to leave around in the rooms where people are doing work, or if there's a common area. And so one thing I have is recent copies of the AWM newsletter. So how many people are AWM members here? Oh, that's pretty good. If you're not a member and you're a student, you can very likely become a free member. There's student chapters all over the country. You can start a student chapter. If you have a faculty advisor, all the student members are free. So you can become a free member of AWM. And there's also institutional members, and the department has an institutional member, which very likely your department has. And then what'll happen is you'll get all of this great information online. You won't necessarily get a print copy of the newsletter, but you'll get emails every month giving you information about opportunities that you can apply for. So I strongly recommend. And now WHAM, the Women in Mathematics program, is organized in cooperation with AWM. So that means that we can kind of cross-advertise the programs, which is what I'm doing here. I'm advertising AWM. And we have Jill Pfeiffer's, another past president of AWM here. And I don't know, do we have any other past presidents here? I'm not sure. No? No. Okay, so my other prop that I brought is something which relates to my lecture series. So I will be talking about post-quantum cryptography. So my daughter said to me, what is with the snake? I have no idea. I did not pick this picture, which is like a snake, a python. Maybe it's Python code. I don't know. But we published this issue. This is a magazine. It's IEEE Security and Privacy Magazine. And it's about post-quantum cryptography, and I was one of the editors. And in here, we have descriptions of all the different kind of mainstream candidates for post-quantum crypto. So later in my slide deck, when you see the list of different things that are the main candidates, there are like really short, readable articles about each one of them in here. So I have 2 copies I'd be happy to pass around and give away, but obviously don't have enough for everyone. Okay, so I have a lot of material. I always have too much, but I always like to try to end on time. So I'm going to get started. So I go till 12:30, right? I can speak until 12:30? Okay. So what I did was to kind of think about what were my goals for this course. What I really wanted you to get an idea of is, first of all, kind of just what is post-quantum cryptography, PQC, and get an overview of current proposals for PQC. But also, when you think about what is PQC, you also have to think about what does it mean to have a crypto system and attacks on it and algorithms and their running times. And so this is a really fundamental concept in computational number theory, is this concept of algorithms and running times. And so yesterday in the preview, I agreed with Serena that it was important enough that she actually started with this notion of complexity. So you should already be thinking about the complexity of algorithms and their running times. And then finally, I chose to introduce in more detail 2 of the current proposals. So supersingular isogeny graphs and lattice-based cryptography. So the way that I decided to divide up the 4 lectures is kind of 2 and 2. So the first 2 lectures will be about supersingular isogeny graphs, And the second 2 lectures will be about lattice-based cryptography. And in each case, I'm going to try to do the first lecture more oriented towards kind of the applications and the motivations and the definitions, just to get an idea of what it is. And then the second lecture is more oriented towards, what are the hard math problems? How hard are these problems? What have we done to try to attack them? That kind of thing. And so in both cases, in the kind of second day, it may, especially if you're an undergraduate, it may involve mathematics that you're not familiar with, and that's fine. Maybe you can just kind of think of it as getting the flavor of the attacks and doing kind of research in cryptanalysis as an area. Okay, so one challenge is that I'm doing a post-quantum crypto course at the same time that Tony's doing a regular crypto course. So normally what I would do is to introduce you to a bit of the history of public key cryptography over the last 50 years. And that includes things like RSA and ECC. But in the interest of time, and also because Tony will be covering some of those topics, all I'm going to do is kind of refer to these things. So some of the things that I'm mentioning here are kind of placeholders saying we are going into more detail on this either in what Tony is doing or what Emily's doing, or we'll come back to it throughout the week. But I have just a couple of slides kind of as an overview, just the basic idea of cryptography, because cryptography is often thought of as just the science of keeping secrets. I mean, you're looking at the Enigma machine, which was for keeping messages secret during the war. But it's a lot more than that now. I mean, zoom forward, 70 years or so, and we live in a very, very fast-paced world where technology is evolving, like the pace of innovation is just accelerating insanely. And with artificial intelligence and everything that's coming through the pipeline, we have very, very technological society. And there's a lot of other aspects of cryptography which are super important. So confidentiality is obviously related to encryption, but authenticity is equally important. So it would be kind of like, I guess the analogy would be, if during the war somebody had an extra, Enigma machine that wasn't authenticated, maybe I should have asked this during your talk, and they sent, a message. I mean, the fact is that's not public key, so they wouldn't have had the right, whatever they're called, the decryption ciphers, or what did you call them? The what? The daily. Yeah, they wouldn't have had the daily key. But the idea is that you don't want people sending messages pretending to be someone else. And so that authenticity is really important in public key cryptography as well. And that's probably a theme that we'll come back to. So the main tools that we use for cryptography today are encryption and kind of encryption, decryption, which goes together, digital signatures, and key exchange. And so what I like to do is, and I have a reason for mentioning all three of these things, and I believe that you're going to go into more detail on these things tomorrow. But the reason that I'm mentioning them now is these are the three tracks for the NIST post-quantum crypto competition that I'm going to talk about today. And so when I say, key exchange, signature schemes, encryption, don't worry, we'll go into more detail tomorrow with Tony's lectures. But it's very important to know that these are the kind of three building blocks that correspond to the functionality that I talked about on the previous slide. So key exchange is for actually setting up, agreeing on a secret key, and the two parties need to be able to exchange information publicly and come up with a key that they both agree on, which is different than what we were looking at with the Enigma. That the daily keys thing, that wasn't being sent through the mail. The daily keys was, being handed to somebody on a piece of paper. So if you have a kind of an offline physical channel for exchanging keys, then you don't need public key cryptography. You can use symmetric key. Whereas what we're talking about when we say public key cryptography with the key exchange is that wanting to have the ability to, for example, you're a first-time customer of Amazon. You go online and you want to establish a secure channel with Amazon. So you're going to go into your browser and there's a secure browser session that you're going to set up. So this is an example of kind of each party has a publicly available key. And, oh, I think I might have taken out the, did I have a slide on the different, yeah, secure, these are the kind of standards that we adhere to actually use cryptography in practice in society. So, for example, if you want to buy something from Amazon, and have you ever seen the little lock up in the corner of the URL? And if you notice the URL, it'll start with HTTPS instead of HTTP. And so those secure browser sessions are using key exchange. So it's, you know, an everyday thing that you actually use. Whereas signed encrypted email, the signed part of that is referring to the assuring the authenticity of the, you know, the sender. But signed encrypted email until recently was really just not used at all in commercial settings. And there's some, you know, I think there's some deployments of it now. Whereas virtual private networking, which is kind of creating a secure connection to, like, say, a corporate site, that's used by all the big corporations. That's very commonly used. And authentication is this, there's this kind of web of, you know, public key infrastructure, which is assured basically by VeriSign and the things that they deploy. And if I understood, Tony, you are going to talk a little bit about public key infrastructure tomorrow as well?
Yeah, a little bit.
Yeah. So all of these are building blocks for basically e-commerce today, and going forward into the future, a lot of different applications that we'll need. And the neat thing is that these are all these public key solutions are all based on great math problems. This is all pure mathematics. If this mathematics wouldn't be done, we wouldn't have these solutions. So it's a really great kind of you know, selling point for the importance of mathematics. And it's also really fun because these are fun constructions and fun ideas and lots of fun algorithms. So the systems that we're familiar with that are used today are based on the hardness of factoring integers. So how many people already know how RSA works? Oh, great, everybody, and then, or almost everybody. And then there's a related discrete logarithm problem in the multiplicative group of the integers. And then what about elliptic curves? How many people already know about elliptic curves? So fewer, but maybe looks like about half. So that's good. So these are all, these are the building blocks for our currently deployed public key crypto. And when I went to Microsoft in 1999, for about the first 5 years I was there, I worked on elliptic curve cryptography and getting it into our products. So implementation and optimization for different platforms, but mostly kind of meeting people and getting them to understand the importance, first just of public key cryptography, but then of elliptic curve cryptography in particular. So as of 2005, Microsoft started shipping, starting with Windows Vista, elliptic curve cryptography basically spread to all of our products, and now it's very widespread across the industry. So this is what exists today, and the disruption, which is causing all of the excitement here, is quantum computers. So the Q in post-quantum crypto refers to quantum computers. So I just want to give a kind of a very, very brief overview of the timeline here, that the ideas leading to quantum computers were originally introduced in the early 80s by several different people, including Manioff, Manin, Feynman, and Deutsch. And if you go to about whatever, something like 15 years later, Shor's algorithm was introduced, which was a polynomial time algorithm for factoring large integers if you have a quantum computer. So the term that we use when we say quantum algorithm, a quantum algorithm means an algorithm that can be implemented using a quantum computer. So when we say classical algorithm, I'm not sure if Serena said this yesterday, but classical algorithm means algorithms that we can implement on normal computers that we already have today, like my laptop or my phone. Whereas quantum algorithm means an algorithm that you can implement on a quantum computer. And polynomial time refers to the running time of the algorithm. And saying polynomial time means it runs in time which is polynomial in the input size. So in this case, I'm going to say this here, and then I'm going to say it a couple slides later. Here's an example. So let's say you want to factor a number n. N is p times q. This is one of these RSA moduli. Well, these days, a minimum size for n, does anybody know roughly minimum size? A little louder.
2 to the 128?
No, that's elliptic curve stuff. Good, glad that you said that. So anybody else shout it out?
200 digit prime?
Not even close, not even close. See, this is great. This is what we're getting at here. At least 2048 bits. So 2 to the power 2048. So like if there was one thing that I would love that you would learn this week is thinking about large numbers. And so that 2 to the 2048, that's a really big number. And so one thing that people...
Is it the primes or is that n?
No, well, I meant n, but there's argument whether it should be 2,000 bits, whether it should be 3,000 bits, that kind of thing. But it's very large, right? So I guess the idea is that when the p and the q, they should be half the bit size of n. They should be balanced. So, but anyway, so if n is 2 to the power 2048, then the log of n is roughly 2048. I mean, it could be a little constant depending on which bit log base you're talking about. But so the idea is that a polynomial time algorithm is something that runs in the running time is a polynomial in the input size. And the input size here is 2048, not 2 to the 2048, because it takes you 2048 bits to write it down. So that's your input size. So hopefully we can kind of keep repeating this message, because it does cause some confusion when you say polynomial time. You think, oh, well, polynomial in n. No, it means polynomial in log n. So that means if it's actually something that runs in time n, then that's called exponential, because n is the exponential of log n. So sorry if that's a little bit confusing, but polynomial time always means polynomial in the input size, which is generally the logarithm. So when Shor introduced this polynomial time quantum algorithm, it still took, for factoring, it still took a little while. In 2001 was the first time that the number 15, factorization of the number 15 was shown using a quantum computer. And so the funny thing about that is that not only that most people could probably factor 15 without a quantum computer, but my understanding is they actually used the fact that they knew the factorization of 15 to demonstrate. So I thought that was pretty funny. And then, so there's a bit more progress, creating. So what this shows, though, is that these two snapshots in time show that there actually exists quantum computers that could already do some computation. But they could do a very, very limited amount of computation because they could only handle a few qubits of input. And so if you zoom forward to today, I think just last month that IBM announced like a 50-bit qubit quantum computer.
Google has 72.
Google, yep, I was just about to say Google's got 72 qubits. So we're inching up there. And so what you should think about is lots of researchers around the world, both in industry and academia and government, are working hard on the problem of building quantum computers. And we don't necessarily even know the state of the art for what various government agencies may be able to do. But in industry, even a lot of, like we just mentioned, Google, IBM, Microsoft have invested a lot in quantum computers. We have what's called Station Q in Santa Barbara, which is a research group working on the topological quantum computing approach. And don't ask me about that because I'm not an expert on that. But that's one of something like about 4 different possible approaches that you could take to building a quantum computer. And then we also have a quantum algorithms group in Redmond, who I've collaborated with, and they have actually released a quantum compiler for quantum algorithms called Liquid. So one of the things that's kind of interesting and important to know, this is really just a side note here for our course, but is that quantum arithmetic is actually very, very different from classical arithmetic. So classical arithmetic, you think about representing numbers as bits and kind of adding and multiplying them together with and OR gates. And so there's a lot of interesting stuff that goes into doing operations efficiently in the classical setting. But quantum algorithms are just completely different. So the basic arithmetic is different because quantum circuits consist of quantum gates, and quantum gates are basically represented by unitary matrices. And so if you want to do some operation, you really have to think about representing your operation as a sequence of applying these unitary matrices. And even that is dependent, what you can do is dependent on the architecture design of the actual quantum computer that's realized if and when it's built in practice. So you could have restrictions like you could only operate on qubits that are next to each other, kind of a nearest neighbor type architecture. Or you could have other architectures that may or may not be realized. So even today we have quantum algorithms which we've proposed or suggested, which may not be able to be implemented if that particular architecture design is never realized at scale. So there's a lot of questions. I actually think this is a fantastic research area, quantum algorithms. There's a lot of arithmetic and stuff in there, and interesting number theory as well. So just this year at AsiaCrypt, with the quantum algorithms group, we published a paper which shows very, very, very precise estimates for the running times of algorithms to attack ECC and RSA. Using quantum circuits, and we actually implemented these algorithms in Liquid, so the quantum compiler that they've built, so we could actually run them and get the kind of precise number of gates and everything. And so the nice thing, this is like the confirming theory with practice kind of thing, is there was actually a paper in 2004 by Proust and Zalka who kind of described the algorithms and predicted that the running times, remember I said polynomial running time means polynomial in the number of input bits. So the running times are something like 4m cubed and 360m cubed, where m is the number of bits. So for factoring, this m should be, like we said, at least today we use 2048, whereas for elliptic curves, today we use m as a minimum of like 256. And the reason I was so happy when you somebody shouted out something about 128 or 200 is that that's the whole reason that you could argue for the use of elliptic curve crypto 10 years ago is that, and I had some slides on this that I took out. We can come back to this after Tony has introduced more about elliptic curve cryptography, because there are sub-exponential factoring algorithms, classical factoring algorithms, and there are no known sub-exponential algorithms for elliptic curves. That's what makes this bit size so much smaller than the RSA bit size. But now when you flip over to the quantum setting, these are quantum algorithms, and you can see that the smaller bit size means that you don't need as large of a quantum computer in order to attack it. So it's kind of flips it around. It's very interesting to me that it turns out this way. So what this basically means is that if you took 256 bits to be your minimum, you would need something like a 1500-bit quantum computer in order to attack elliptic curve systems that are used today. If we migrate up to 384 bits for elliptic curves, then that's a little bit better. You'd need more than 2000-bit quantum computer in order to attack it. But just as a side note, part of what we did in this paper, I think why it was published in AsiaCrypt, was just to give a quantum algorithm for finite field inversion in this paper. So that's a snapshot. That tells you today, classically, we know how to do all kinds of very advanced things. But today, it was still, improving the state of the art to give an algorithm for just finite field inversion. So that, hopefully, I want to let that sink in. Finite field inversion. So that's, well, I mean, I'm not sure if I have the right level in mind here, but finite field inversion is just, you have an element of a finite field, and you want to find its multiplicative inverse. So you can do that, for example, in like log p multiplications if p is the size of the field in a classical setting. And in the quantum setting, there's a lot of work to do to actually design circuits to do very, very simple things, which I think that's why I think it's such a great research area. Okay, so here's the timeline for elliptic curve cryptography kind of possibly being phased out. What we're seeing is that in 2006, as I mentioned, the requirements were set for the use of elliptic curve cryptography. And then zoom forward to 2016, CNSA requirements increased the bit length from 256 to 384. That's why I had both of those numbers on my previous slide. And it also advised that adoption of ECC was no longer required. So that was kind of a key point. And in 2017, NIST launched this international competition to select post-quantum cryptography solutions. So now we've come to the point in the talk where we can really start thinking about what are the PQC options. So again, so what do we mean by post-quantum, right? Post-quantum means that, let's imagine a future where we have a quantum computer. The quantum computer can, as we know from Shor's algorithm, be used to give polynomial time attacks on all of our existing currently deployed crypto. So that will be bad. So imagine if, like today, there was a quantum computer and an attacker could go and collect all of your credit card numbers when you buy something online or something like that. That's what we want to avoid, because the problem is it takes a lot of time to replace existing systems. So now what we're doing is we don't know when a quantum computer will be built at scale. One that's, let's say, 1,500 bits or 2,000 bits, like I showed on the previous slide, would be necessary. So let's say that date is going to be 20 years in the future. We don't know. Maybe it'll only be 10. But from an industry point of view, we know that whenever we have to start changing our systems, it's going to take, typically we estimate like 5 years to change over systems. And so we don't want that quantum computer to come into existence, before we have a chance to start, ripping things out and putting in new things. So that's kind of that. I say that a little bit tongue in cheek, but that's kind of the idea is that the NIST post-quantum crypto competition, which is starting this year, is planning for the future. They say that the competition itself will take roughly the next 5 years. So think of a process now that's, it's an international competition. So NIST is a National Institute of Standards and Technology, is an agency of the US government, but the competition is international. And so we have submissions from people from all over the world, teams from all over the world, and now it's going to be a very open process to evaluate all of these submissions. And let's say it takes something like 5 years. The other NIST competitions that have happened during my time at Microsoft have taken much less than 5 years. So the hash function and the block cipher competitions, I think they took no more than like roughly 2 years. But this is a bigger deal for reasons that you'll see kind of as we go along. And so if they take 5 years, then what would happen as an outcome? They will propose some standard, and then everyone in the world, really, but certainly in US industry, will start to try to build to that standard. So that's the process that we're trying to influence here. And one of the things that I really enjoyed about going to Microsoft Research for my career is that I've been much more involved not only in doing mathematics research, but actually working on things that lead to real changes and impact in society as well. And those kinds of changes happen through this kind of process, like a government agency leading a public open competition, academics exchanging information and interacting with industry and government and other researchers. So this, I can't emphasize enough the importance of this NIST PQC competition. So maybe I'll pause and see if anyone has any questions about what I've said so far. Go for it.
Why are so many bits required for a quantum computer compared to like a classical computer?
Okay, so that's a little bit, I think it's a little bit the opposite of what you wanted to say. So what happened, like I didn't give running times for ECC in the classical setting. I said, like, I took out those slides. Maybe I'll bring them back after Tony has introduced the typical ECC system. But an exponential time algorithm would mean that you would need like time like 2 to the 2048 instead of some polynomial in 2048. And, or is that what you were asking?
I was thinking of, like you said, it would require a quantum computer with like 1,500 bits to attack ECC.
Oh, I see. Oh, you just need room to do computation. So even when you think about a classical computer, like how do you operate on bits, you need like memory allocation. You need to put things in different places and then access them and put them together.
So you just need more for quantum?
Well, it's not that many. I think it was 6M, I think, or 3M.
What's the comparable for a classical computer?
Yeah.
Very comparable.
Yeah. So just think about it as like, there's one extra requirement is that all quantum algorithms have to be reversible. So once you've done the computation, you have to actually be able to reverse it. So we could take less room, we could take less memory if we didn't have to reverse it. But if you didn't reverse it, you would like disturb the quantum state. It would be like, measuring, and you would collapse it. And so in some cases, the algorithms, they actually need more bits or more memory because of the fact that you have to reverse it. Sorry, I misunderstood your question to begin with. Other questions? Okay, so here's the current kind of slate of candidates. There's 30-something submissions to the NIST competition, and there's only 5 items here. So you say, why are there only 5? A lot of the submissions fall into buckets, and these I'm just calling out some of the main buckets. This is not exhaustive. But I wanted to also, again, give you a bit of an idea of the timeline here. So code-based cryptography was actually introduced by McLeese, who's a professor at Caltech, in around 1978. And it was a crypto system that uses error-correcting codes, which is something which has nothing to do with cryptography, even though it's got the word codes in it. And error-correcting codes to create crypto systems. The basic hardness assumption there is hardness of decoding random linear codes. And most likely I'm not going to have time to talk about this in any of my lectures this week, but if anybody wants to talk about coding theory, that's actually what led me kind of from algebraic geometry into cryptography. So coding theory, I think, is a really interesting topic. And it's really neat that this is one of the main proposals. But the code-based crypto proposals require two kind of hardness assumptions. One is that decoding random linear codes is hard, which so far it's hard. We don't have quantum or classical sub-exponential algorithms for. But secondly, in order to implement such a system, you have to kind of like secretly disguise a special linear code as a random one. And so you also have to assume that you can't undo this disguise and figure out the special structure of the code that you're using. So those are kind of 2 basic hardness assumptions. And one of the issues with code-based crypto is the absolutely huge key sizes that it requires for security. So a second type of proposal are multivariate crypto systems, which have evolved over the last basically 30 years or so. you can just think of multivariate cryptosystems as being systems where you're relying on the hardness of finding solutions to large systems of multivariate equations, so many variables, many equations, and nonlinear. So not linear equations, but so multivariate crypto is relying on the hardness of solving those type of equations. Hash-based cryptosystems is actually based on like Merkle hash trees, invented around the same time period, which is more kind of a symmetric key type philosophy. So lattice-based cryptography is very nice that we have Joe Pfeiffer here to speak about NTRU this afternoon. And I will speak, as I said, lectures 3 and 4 will be related to lattice-based cryptography. And so lattice-based cryptography basically started in the mid-90s with the NTRU proposal from Hofstein, Pfeiffer, and Silverman. And then the final item that I'm including on this list is called supersingular isogeny graphs. And this is a proposal that I made with two co-authors, Dennis Charles and Eyal Goren, in 2006. It was actually presented in 2005 at the NIST hash function competition. And this is the proposal which, as you could see from the timeline here, is certainly the youngest out of these. So, you know, like McLeese, that's been around for 40 years now, whereas supersingular isogeny graphs has only been around for 12 years. But it is the one that has the most interesting number theory in it. And so that motivates me to want to talk about it more. Okay, so because we're going to be hearing about lattice-based cryptography more later this week and this afternoon, I'm going to skip over that in the interest of time. So I have about 20 minutes left. So my goal is to really get you to get an idea of what are supersingular isogeny graphs, because those words, they don't sound very elementary, right? So what is supersingular? What is isogeny? What is a graph? That's what I would like to get across to you right now. So the one-line version of what we introduced in 2006 is a new hard problem, which was finding paths in a particular graph, this supersingular isogeny graph. So first, obviously, we need to talk about graphs. So unfortunately, in society, we use the word graph to mean lots of other things, including like little charts, you know, bar charts and things like that. That's not what we mean here. A graph is often denoted by G, which is V comma E, a collection of vertices and a collection of edges. So you could think of a finite graph as being something you can describe by saying what all the vertices are and saying what all the edges are. But if it's a really large graph, that might be kind of hard to do, right? So it's one thing to think about, especially in this kind of mentality of crypto, where you're thinking about algorithms and running time and how much space does it take you to represent each thing and how can you do that efficiently, is it's nice to have efficient labels for vertices. And it's nice to be able to specify crypto systems without writing down the whole object. Assume that the object is going to be so large, like this graph is going to be so large that you can't write down the whole thing. And so you want to have crypto systems which will allow you to work on part of it without having to write down the whole thing from the beginning. So a graph, there's several properties of the graph. I'm kind of, this is giving away some of the punchline here, but the properties of the graph that we use in this construction that are very nice are, well, one is the fact that you can label vertices, so that's very nice. Another, with like a recipe that's easy to compute. So another is that these graphs are k-regular and undirected. Undirected means edges don't have a direction. That means you can go either direction on an edge. It's not a one-way path. And k-regular means out of every vertex, there's exactly k edges coming out. And expansion, optimal expansion is a very nice, interesting property. Let me just say a few words about it. I'd be happy to talk more with people about this. Expander graphs have the property that you quickly acquire lots of neighbors, right? So you can give an elementary definition of expander graph in that sense. But the kind of consequence of having good expansion, there's a specific expansion constant which measures the expansion property of the graph. And the consequence of having good expansion is that when you take walks in the graph, you quickly get to like a uniformly random location. So this is actually a very key concept in theoretical computer science, and it's used all over the place in all kinds of proofs. And so having optimal expansion is also good for cryptography because you quickly get to like a uniformly random looking place. And so, so finally, the very, very key property of these graphs, supersingular isogeny graphs that we will use, is that this is the hard problem, is that there's no known efficient routing algorithms. A routing algorithm is, here's one random vertex in the graph, here's another random vertex in the graph, how do I get from here to there? So I hope you can see from my description that that is a very, very accessible problem, right? That is very easy to explain. Just keep in mind also, I didn't want to have to write down the whole graph, right? So it was huge. So you're not looking at the whole graph in front of you, but just imagine somebody gives you one vertex, now they give you another vertex, and you have to find a path between them. So that's the hard problem in this area. So now let's go into the motivation. Why did we suggest this at the time, 2005? Because NIST was looking for a new solution for a hash function. So this is an opportunity for me to do 3-5 minutes here on cryptographic hash functions. So who already knows what a cryptographic hash function is? Oh, good. So most people. Hash functions, I'll do it very quickly then. Hash functions just take a sequence of bits and they output another sequence of bits. We want them to be efficient to compute because they get used in all kinds of cryptographic protocols all the time. We want them to be unkeyed, so meaning you can specify them publicly and anyone can evaluate them. And the two properties, there's more properties that you might want from a cryptographic hash function, but two basic ones that you absolutely obviously need are what are called collision resistance and, sorry, I don't have it written, preimage resistance are the two. But you would also like it to have kind of a uniformly distributed output because you don't want to have a bias in the output. Cryptographic hash functions are used like pretty much everywhere. The security of almost all crypto protocols rely on a hash function, which is usually, ironically, modeled as a random oracle. They're used for things like password verification, integrity check of digital content, like signed hashes, encryption protocols. The message digest is like signed hashes. And in Microsoft source code, there were, at the time when MD5 had to be replaced, there were more than 720 different implementations of MD5 in Microsoft source code, even at that time, which is more than 10 years ago. And the joke is that, and not all of them were even implementations of MD5. At least one of them was an incorrect implementation of MD5. So collision resistance, what does that mean? That means if you have a hash function which is publicly specified, that it's hard to find two distinct inputs, x and y, which hash to the same output. And again, if you think about this, this definition here, where it just takes n bit strings of length n and sends them to bit strings of length m, well, if you're using this as like for a message digest where you're taking, several gigabyte, file and you're hashing it down to some short hash, which is like 128 bits, you might think, oh, wow, there have to be a lot of collisions, right? Because this is a really, really big file and this is a really short label. But the issue is that if m is 128 or 256, it's still, that's a huge search space to the 256 to the 128. So even though, of course, there will be collisions, we just want it to be very hard to produce a collision. So that's the issue. And then going back to the other definition, which I thought was important, which is preimage resistance. Preimage resistance means that given a particular output, can you find an input which hashes to that output? So clearly, if it's not preimage resistant, if you can find preimages, then you can just run it twice and you can find collisions. So that's a stronger assumption than the collision resistant. Okay, so here's the application. Here's why we suggested supersingular isogeny graphs. Because you can take this idea from computer science that you can walk around a graph and end up at you can walk around an expander graph and you can end up at a roughly random location. So you can take that idea and now we can use that to create a hash function. So the hash function would be, you have some input bit string. You're going to take that bit string, you're going to divide it into blocks, and each block is going to be used as directions for walking around the graph. And at the end, after you've read the whole bit string, you are standing somewhere on some vertex. And the output of the hash function is just going to be the label of the vertex. So that wherever you end your walk, then you output the label. That's the hash function. And one thing that's important is that backtracking is not allowed. Because if I go forward a step and now I just go backwards from where I came, then I could just go forward again and that will automatically create collisions because you could do that backtracking in like 2 different places and you'd still end up in the same endpoint of the walk. So this was the kind of basic idea for creating a hash function. So now we should think about what does it take for this hash function to be collision resistant and preimage resistant. So the nice thing, that we took this idea from theoretical computer science, which is very common, of walking around expander graphs to create random outputs. But now we need an extra property. And the extra property is that it's actually hard to find your way back. Think of like the 2 endpoints being the endpoints of a walk, and what you need is, Hansel and Gretel were walking in the woods and they were dropping breadcrumbs, and so they knew their path, and now they could go back. But if you didn't do that walk yourself and you don't have those breadcrumbs, so that's what you're looking for, is the breadcrumbs in the woods. So here's a really bad idea. What about taking a graph which is a hypercube? So hypercube is just the labels are all the bit strings of some length, and then two vertices are adjacent if they just differ by 1 bit. So now here's 1 bit string, this is 1 vertex, here's another bit string, it's another vertex. What do you do to get from one to the other? Yep. Just flip every bit that's not the same. And there's lots of different walks, and you've found all of them very well. There's probably an exponential number of walks, actually. So any graph that can be embedded in a hypercube is a bad idea, because then that means that you can do routing easily. So you don't want something like that. So what do you want instead? So let me see. I think in the interest of time, I'm going to skip over. These are the kind of colliding walks stuff. So here's the proposal that we made. So supersingular isogeny graphs are the following. The vertices are now going to be supersingular elliptic curves defined over a finite field or a quadratic extension of a finite field. So now I realize that about half of you had not worked on elliptic curves before. Serena introduced the group law yesterday. Tony's going to talk about elliptic curve cryptography tomorrow. So don't worry if you don't already know a lot about elliptic curves, because the funny thing is, this is actually a completely different use of elliptic curves. You barely even need to know the group law. You need to know other things for this application of elliptic curves. So just think of an elliptic curve as being given by an equation, y squared equals x cubed plus ax plus b, where a and b are just elements of the underlying base field. The underlying base field is going to be a very large finite field. So it's either going to be the finite field of p elements or a finite field of p squared elements, where p is going to be of cryptographic size. So because P is of cryptographic size, so in particular, it's definitely not equal to 2 or 3. And 2 and 3 are the problem cases where you can possibly need to have more complicated Weierstrass equations for elliptic curves. But if P is not equal to 2 or 3, we can always use this is called the short Weierstrass form of the equation. And so given this short Weierstrass form, here's a really nice fact. The J invariant of the elliptic curve can be expressed in this form. So this is just a rational function of a and b, 1728 times 4a cubed over 4a cubed plus 27b squared. And that is a very nice label for all of the vertices in our graph. So I haven't told you a lot about the theory of it, and in particular, a supersingular elliptic curve is it's kind of an extra special property. So I'll say a little bit more in a minute. So the edges are going to be now isogenies between these elliptic curves. And so kind of the minimum, the way I see it, the minimum that I need to really define in order to tell you what these graphs are, it kind of gave you this was a very, very brief definition of an elliptic curve, just giving you an equation that represents it. It wasn't really a very good definition. But I need to tell you what supersingular means. I told you what the J invariant was. Those are going to be the labels. And the isogenies are going to be the edges. So you can see, if you haven't had any course in algebraic geometry, this is already a bit of information that you need to digest in order to know what these graphs are. But at a very high level, you can still kind of understand what they are if I just tell you what the recipe. But one thing that you don't get from the high level is the beautiful properties of this graph that come from very, very deep theorems in number theory that are very beautiful. So for example, the fact that this graph is an optimal expander graph, which we call a Ramanujan graph, is a very, very deep set of theorems and associations in number theory. Even just the size of the graph is called the Eichler class number. That's also a beautiful concept in number theory. And even the fact that it's an undirected graph, that we can associate an isogeny with its dual, that also requires some information. So in other words, what I'm trying to say is I think that at an elementary level, I can tell you what the graph is. And then you kind of have to believe that there's all these theorems that give you the nice properties of the graph, because definitely we won't have time to cover proofs of these theorems in this course. But sticking with this kind of high-level version of the description, I will tell you that the Eichler class number tells you that there's something like p over 12 vertices in this graph. So if p was the size of the finite field that you took, so that means if you take p to be roughly this size, 2 to the 256, and this afternoon in the review session, we'll talk about algorithms that are, Serena's going to talk about kind of square root algorithms for attacking these graphs. So that's why you can think of taking 2 to the 256, or there's other applications, there's other settings where you take it to be larger than 2 to the 256, but at least that big. And then also, I've given you the formula already for J invariants, and I've told you that they're regular graphs. They're actually, if the degree of the isogenies is L, they're going to be L plus 1 regular graphs. And this Serena will also go over this in the review session this afternoon, figuring out why that's true. So I'm going to kind of skip ahead. Oh, I think I missed my slide on the isogeny. So what is an isogeny? That's the last thing that I didn't tell you. So an isogeny is actually, there's two different things. There's separable and non-separable isogenies. And separable isogeny is when the size of the kernel is basically co-prime to the characteristic. So what I'm going to do is I'm going to assume that we have a prime L, and is different than P. Remember, P is the really large prime. And so in particular, like I said, P is not equal to 2. So I can take L equals to 2, and we can think about what do we get if we take L equals 2 in this graph. So in this graph, what does it mean to be a 2 isogeny? A 2 isogeny just basically, this is a statement you can find, for example, in Silverman's book on elliptic curves. Isogenies are essentially characterized by their kernels. And what an isogeny is it's a homomorphism between these kind of algebraic groups. And so you can think of it as just being taking the group and quotienting by some subgroup. And so an isogeny is just, an L isogeny is just quotienting by a subgroup of size L, if L is prime. So here L is 2, so we're just going to quotient by a 2 torsion subgroup. So that's an isogeny, and that's one of those correspond to edges. So the formula for isogenies was, for elliptic curves, was given very explicitly by Velu in a short paper. I think it was actually in the 70s. It was quite a while ago. And here's the formulas. And again, I think Serena's going to go over some of this in the review session. That given an elliptic curve E1 with this equation, with this J invariant, here's a 2 torsion point on the elliptic curve. Again, this is kind of skipping ahead because we haven't really talked that much. But I'm just trying to give you an idea how incredibly concrete it is. Here is this, if you quotient by that subgroup, here is the elliptic curve that you get as the output. And I'm not sure, maybe even Allie might be doing some of this material in her review session on Wednesday. And here is the map that goes from this, here's the actual isogeny. And so these are it's supposed to give you an idea that there are very, very concrete maps here. Okay, so we're almost at lunchtime, and I always like to end with a picture. And so let me just say a little bit about this picture. So this picture appeared in Science magazine in 2008. It was written by Dana McKenzie based on a talk that he heard me give at the joint math meetings. And this is a supersingular isogeny graph. And so he wrote this article because of the hash function competition that NIST was running, and this proposal that we had made for hash functions. And this is taking the prime p equals like 2521. So you could see from my Eichler class number formula that the number of vertices should be roughly p over 12. So take 2521, divide by 12, you're getting something like 200 vertices. So there's like 200 little vertices here. But these are the edges when L equals 2. So we took, this is the, it's a 3 regular graph representing the 2 isogenies. And so what you're supposed to see here is that even for a very, very small graph, right? This is a graph that's small enough that we could show you the whole thing on a page. If you take 2 random vertices, like take this one and this one. And so the question is, how do you find a path between them in this maze? And again, this is small enough that we even wrote down the whole thing. And so here we actually drew out a path so that you could see that this blue thing was a path between these 2. And here is actually a cycle, which is what corresponds to the collisions in the hash function. So this should give you an idea that these supersingular isogeny graphs are very, very kind of very messy, right? They're not at all like a hypercube, for example. And here I also have the picture in here too. So the interesting thing is, so I kind of wanted to kind of conclude on that. On that note, so first of all, one of the reasons that I did the slide talk is so that you guys didn't have to take notes or anything. The slides will be online. You can go back and look at anything that you want to look at. And in one of the things that I wanted to comment on is that these supersingular isogeny graphs are an example where you have this incredible confluence of this beautiful mathematics, all of these deep theorems in number theory that you get to create this beautiful object, which is a Ramanujan graph, and it's also easy to actually work with. You've got the labels for the vertices. You can walk around the graph very concretely. And so for us, this was really fun that we proposed this in a particular context, which was hash functions in 2005. And now we zoom forward into the future. We didn't realize that it would end up being a candidate and a submission to the NIST hash function competition for post-quantum crypto 12 years later. So these are two different NIST competitions. And so it was, a proposal based on mathematics, which is now being used in kind of a different context. And so there was a little confusion about the history, so I just added this slide so that in case you're looking at the papers or you want to look these things up. So our original paper with Charles and Gorin was presented in 2005, and it's available on ePrint. I actually have a copy also if anyone wants hard copy. And after that, there were two papers that were put up on ePrint, which are often erroneously cited in this area now, because they actually have nothing to do with this field. So by Kuvenya and these two Russian authors, Rostovtsev, Stolbanov, and both of these have to do with the ordinary case. And the interesting thing is that graph that you get from considering ordinary elliptic curves is completely different. It's not a Ramanujan graph. It has a different shape. It has the shape of a volcano. It doesn't have any of the nice properties that I listed. And it's a completely different kind of irrelevant thing. So if anybody points you to these papers, you can just ignore them. They do not have to do with supersingular isogeny graphs. And we have the supersingular case, which is still an open, hard problem. And tomorrow what I plan to do is to talk about the hardness of the problem for supersingular isogeny graphs. Thank you.